Stability heatmap view shows the stability of the selected region and provides region adjustment by directly clicking.
This is a picture of a Tableau visualization within the browser. The data behind the visualization does not exist here, and Tableau is not running. This is just an image. However, parts of this image are fully interactive. Please join our presentation to see how we can share interactive visualizations across the web, free from any dependency on data or visualization application.
A testing environment for continuous color maps. Many other fields in the computer science do it, we should do it too. With our work, we introduce the approach of using test functions as a standard evaluation method. We present a test suite for continuous color maps implemented in the CCC tool. Adapt the task to your requirements at the interactive testing section and observe them at the testing evaluation section.
Out-of-distribution samples refer to the test samples not well covered by the training data, like these black cats. They are misclassified with high confidence due to their black bodies. To explain why these samples are out of distribution, we developed OOD Analyzer, a visual analytics tool which provides an ensemble detection method and a grid-based visualization to detect and analyze out-of-distribution samples.
We have seen many visualizations for tree data structures, but when showing changes in trees over time, some focus on displaying hierarchy, while others highlight their changes. With split streams, we combine two approaches and their individual benefits. We evaluated our method in a user study and consider it a general-purpose method for the visualization of dynamic hierarchies. Our JavaScript library is openly available. VIS is a visual support system for the development of visualization algorithms. It has live compilation, automatic version control, predefined interactions, and tools for visual parameter analysis. By displaying the complete history of the algorithm, users get insights into the correlation between source code changes and visual differences.
The classifier trained on the historical data may fail to classify the incoming data when the data distribution is changing. This phenomenon is called concept drift. To handle the concept drift, we developed the Drift VIS, a visual analytics system to help the expert understand when, where, and why the drift happens, and update the model to improve performance.
CMed is a visual analytics framework for exploring medical image data annotations acquired from crowdsourcing. CMed can be used to visualize, classify, and filter crowdsourced clinical data based on a number of different metrics such as detection rate, logged events, and clustering of the annotations. CMed provides several interactive linked visualization components to analyze the crowd annotation results for a particular video and the associated workers.
Entities and their changing relationships can be modeled more precisely as temporal hypergraphs, but hypergraph models are difficult to explore and refine. By leveraging domain-specific geometric deep learning models and a new multi-level hypergraph visualization, our technique allows for the direct integration of domain knowledge into the machine learning process. The multivariate hypergraph model structure can be analyzed on different abstraction levels. Simultaneously, experts can integrate their domain knowledge on the fly, and then explore the refined machine learning model.
How many clusters can you see in these images? With different visual encodings in scatter plots, our perception of cluster count changes. We developed models that consider how visual density influences cluster perception. Further, we demonstrate using a threshold plot to optimize the saliency of clusters.
As data is changing, our understanding of data should be updated correspondingly. Based on machine learning approaches, we formulate a drift level index to monitor the evolution of multi-source data, which allows users to capture and reason significant changes from time series data. The proposed visual analytics system is called Concept Explorer. More details can be found in our talk.
Confusion flow is an interactive visualization for the performance analysis of classification models. It introduces a novel temporal adaptation of the confusion matrix, which lets model developers compare the learning behavior of multiple classifiers over time. Find out more about confusion flow in our talk or in our TVCG paper.
We present NL4DV, a toolkit that helps prototype natural language interfaces for data visualizations. NL4DV provides a high-level Python API for interpreting natural language queries. The API automates the core tasks of processing natural language queries to infer relevant information and determine appropriate visualizations, allowing visualization developers to focus more on designing and implementing the user interface.
Hands-on cybersecurity training represents a domain where visual analytics can significantly improve the impact of teaching process. We describe this new application domain and introduce a conceptual model that can serve as a framework for the development of analytical visualizations. Unified training lifecycle will be discussed from the perspective of different user roles.
While meetings are an essential part of everyday business life, most calendar visualizations are not designed for retrospection. We present a tool consisting of 4 coordinated views that integrate into the user's daily workflow and are designed to promote self-awareness about past scheduling decisions. We discuss the insights gained from an internal user study and from a field deployment. We also discuss how we strongly inherit from the principles of personal visual analytics despite targeting a professional environment.
In this study, we designed a system named Causality Explorer to facilitate the causal analysis. Users can explore the causal graph to perceive the causality and its uncertainty, validate the causality with the raw data, and apply the confirmed causality to what-if analysis.
In this talk, we introduce CallFlow, an interactive visual analysis tool that provides a high-level overview of performance profiles from large-scale scientific applications. CallFlow visualizes the flow of resource of a program execution as a Sankey diagram to detect performance bottlenecks in parallel codes. CallFlow simplifies these calling context trees based on semantic information by constructing supergraphs.
In our paper, we address the problem of navigating complex multiscale and dense environments, such as these molecular models. We present a technique for browsing a model by clicking on textual labels, which we call hyperlabels. This allows the user to intuitively navigate the hierarchical organization of the model. For more details, read our paper or watch the talk.
Taylor-Coyer flows is a turbulent fluid motion created in the gap between the two rotating cylinders. The traditional reason-based methods are only able to capture the small-scale coherent structure. The detection of the large structure depends on the 2D cross-section, which is not the true configuration. We adapt the feature-level set methods and the density estimation to combine multiple attributes and use them as the filter to separate large and small-scale structure.
Visualizing class separations is used in applications such as classification and clustering. However, many dimension reduction techniques are limited due to the issues of separability and interpretability. We propose a visual analytics framework to support the exploration of nonlinear complex separation structures with the power of locally linear separations.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend your data. With Tableau, you can keep on asking questions in the data until you discover the root cause. Tableau, answer questions at the speed of thought.
Spot SDC is a visualization system that helps researchers understand the resiliency of HPC computation kernels to silent error corruptions. It gives users multiple perspectives of details with different granularity about the impact of SDC on an application's output. It also provides novel insight into how silent error propagates through a program's execution.
Progressive visual analytics provides intermediate results in the middle of computation to address a long computational delay. However, such intermediate results are uncertain, so findings from these results can turn out to be incorrect for the entire data. In progressive visual analytics with safeguards, we suggest to risk the uncertainty, but we allow humans to leave safeguards every time they risk the uncertainty.
We present Lyra 2, a system for designing interactive visualizations by demonstration. To design interactions in Lyra 2, users directly manipulate the visualization canvas. The system interprets demonstrations using heuristics and suggests possible interaction designs. We find that Lyra 2 enables rapid prototyping of an expressive range of interaction designs. We're excited to share this work with you.
Digital humanities present great opportunities for testing new visualization approaches and evaluation techniques. However, and given the diffuse character and novelty of the field, it may also be intimidating for novel and senior researchers willing to get started in the discipline. In this paper, we propose a data-driven analysis of visualization for the digital humanities to identify key themes, authors, and relevant publications. So if you want to know more, please read our paper.
We present VIS, a tool for visualizing hypergraphs where edges can connect any number of nodes. VIS is the first technique to display hyperedges with no overlap or crossing. Vertices are represented as rows, time periods flow from left to right, and groups can be shown on the left. We designed it.
Hello, welcome everybody. Welcome to the LDAV paper session on rendering and displays. I'm Markus from KAUST, and we'll have 3 very exciting talks in this session. The first talk is entitled Interactive Visualization of Terascale Data in the Browser, Fact or Fiction. The authors are Usher and Valerio Pascucci from the Ski Institute at the University of Utah. And their paper has also received the Best Paper Honorable Mention, so congratulations. And the talk will be given by Will. Will, please.
Hi, I'm Will Usher, a grad student at the Ski Institute at the University of Utah. And in this talk, I'm going to present our work on achieving interactive visualization of Terascale data entirely on the client in the browser. So as a spoiler alert, the answer to this question is that it's fact, if you make the right algorithmic and data compression choices. So first, let's take a look at why we'd want to do fully client-side visualization. From a developer standpoint, we can target a single standardized environment, which is cross-platform. So essentially the browser becomes our cross-platform portability layer. Deploying our code through the browser also makes it widely accessible to users, so anyone with a browser and network connection can run it. Specifically for client-side visualization, running our app on the client lets us get low latency interactions. So we're processing the data locally on the client. We don't have to go back and forth to a server, so it will reduce latency that the user has. And it will also let us save money in terms of deployment costs, where we don't need to run expensive backend servers to perform computation. So if we consider a large-scale deployment like the New York Times COVID tracker, if this needed some expensive compute to be run, doing that or paying for that can be quite significant. Prior work has deployed VIS apps on the client, typically using WebGL for rendering or processing, but these are somewhat limited by the state of the browser ecosystem at this time. So you lose access to native libraries, and JavaScript performance is kind of subpar, but the local processing alleviates latency to the user. On the other hand, applications using a remote server for processing can deliver powerful computation, since you have access to pretty much arbitrary compute on the back end, and you can leverage the existing native libraries that you're familiar with on the server, but there can be costs with latency and server costs. So to summarize these challenges in bringing VIS to the browser, the widely used libraries that we have on native applications are typically unavailable. The performance of JavaScript is not really where we might want it to be. There's no solution for GPGPU. WebGL is really just a rendering API. There's no compute shaders. And WebGL is also kind of lacking features that we want for high performance rendering. However, the browser ecosystem has been evolving, and these issues can actually be addressed by current and upcoming technologies, specifically WebAssembly and WebGPU. WebAssembly is a bytecode format for a VM integrated natively in the browser, and it's almost as fast as native code. Unlike Java applets and Flash, it's embedded natively in the browser, so it's shipping today in the browser and is available. And it's also targetable from multiple languages. So C, C++ can be recompiled with mscripten. Rust can target it. C#, Go, Swift, quite a few languages. Specifically for client-side applications, though, WebAssembly modules can also achieve much tighter integration with JavaScript. And JavaScript is actually able to access data from the module directly. So the example I show here on the left is a C wrapper that we put over the Lost Tools API so that we can call it from a WebAssembly module in JavaScript. And on the right side, we're calling into that module to load a LiDAR data file. And what I want to highlight is here, where after loading the LiDAR data, our JavaScript code takes a view of a subset of the WebAssembly memory buffer. That's that heap F32 buffer. We take a view at an offset of it that contains the actual loaded point data. So we can just get it without copying. WebGPU is a modern high-performance graphics and compute API for the web, and it's in development by the major browser vendors and is available in preview builds right now, but it's kind of on the way. It's definitely less stable than WebAssembly, which is a released product at this point. But WebGPU supports compute shaders, storage buffers, and storage textures, so it lets us really have powerful GPU capabilities in the browser. And you can kind of think of it similar to DirectX 12 and Vulkan, though it's much easier to use than those APIs. So we first evaluated WebAssembly and WebGPU versus their native equivalents on a few common SciViz tasks, which I'll discuss briefly before getting to our main contribution. So here we evaluated using native libraries compiled to WebAssembly to load different data formats. So on the left, we're loading TIFF stacks for connectomics data, and on the right, we're loading LiDAR files for LiDAR visualization using Lost Tools. So the main takeaway here is that these sorts of data file processing tasks on the CPU can be about 2 to 4 times slower than the native equivalents. And these are all run on a Surface Pro 7. We also compared a textbook serial marching cubes implementation in C++, JavaScript, and WebAssembly. And we find that in Firefox, our WebAssembly version is actually just 1.5 times slower. And it's 3.2 times slower in Chrome. And this benchmark is run on a sampling of 100 random ISO values over a range representing kind of common visualizations. We also tested a textbook data parallel marching cubes, where we use prefix sums and stream compactions to find and filter the active voxels and output the vertices. And while we don't see much of a speed up over the serial version on the Surface Pro 7, we do see quite a significant speed up on the RTX 2070, up to 7 times faster than WebAssembly and 5 times faster than native C++ version. The most important thing that I want to mention here, though, is that the performance of WebGPU is on par with the native Vulkan implementation, though we do see some overhead on smaller data sets. Finally, we compared parallel decompression performance on the GPU by porting ZFP's CUDA decompressor to the Vulkan and WebGPU. And we compare this against the CUDA implementation on the RTX 2070, and we have to compare it against the serial CPU implementation on the Surface Pro 7. So obviously CUDA is not available, but ZFP also doesn't support decompression with OpenMP, so we only have the serial one to compare against. While our implementation trails the CUDA one quite a bit, we still find again that Vulkan and WebGPU perform about on par, and even on the Surface Pro 7, we do start seeing improved decompression performance, which is exciting. So hopefully by now you're motivated that WebAssembly and WebGPU can potentially enable real SciViz apps in the browser. And so now I'm going to discuss our GPU-driven isosurface extraction method for block compressed datasets, which we specifically developed for interactive isosurface computation on large volumes in resource-constrained environments like the browser. I'll mention here a very abbreviated summary of prior work on parallel isosurface extraction. Of course, this is a large field, and they cannot possibly cover everything in this short time. So Daikin et al. Presented a GPU-based method leveraging prefix sums and stream compaction using histopyramids to compute the vertices in parallel for each block. And this computational approach of prefix sums and compaction is followed by most existing methods today, though of course today you would now use CUDA for the kernels and something like thrust or VTKM for your parallel primitives. Schroeder et al. Presented flying edges, which processes the edges in parallel to efficiently output an index triangle mesh instead of a triangle soup. And Liu et al.'s parallel marching blocks block-based work decomposition is kind of similar to our method. Given the 3D volume, they can process blocks of voxels in a thread group, shown in blue, and within each thread group, a thread is assigned a dual cell, which is shown in purple here. So in contrast to our approach, though, they assume that the entire volume can be stored on the GPU in a single 3D texture, and they only use the block decomposition to accelerate computation by skipping unoccupied blocks. Within each block, they perform flying edges. So there are a few observations that motivate our block-compressed marching cubes method. First, isosurfaces of interest tend to occupy sparse subsets of the volume, and users frequently explore neighboring ISO values when they're interacting with their dataset. Third, CFP's fixed rate mode can decompress individual 4-cube blocks without decompressing the entire volume. And finally, web GPU performance is on par with native Vulkan performance, and so offloading a significant work to the GPU will be beneficial. So let's take a look at our algorithm at a high level. Our method works by moving the isosurface computation, decompression, and cache management onto the GPU to parallelize the work. And key to this is our fully GPU-driven LRU cache, which I'm going to discuss in more detail later. So starting from an existing cache, which was used to compute a previous surface, or an empty one if this is the first surface we're computing, we want to compute the isosurface shown in A. The cache contains a growable number of slots within which a decompressed block can be stored, and it's initialized to have some user-specified capacity. In B, we find the blocks that contain the ISO value or are needed to provide neighbor data for those blocks that contain it. In C, we determine which of these blocks are already in the cache and which must be newly decompressed and added. In D, the active blocks are filtered down to just those that will output vertices. In E, we perform a prefix sum and compaction to compute the IDs of those blocks. In F, we compute the offsets that we're going to write each block's vertex data out to. And in G, we compute and output the vertices. So now let's take a look at the key steps of our method in some more detail. Similar to Liu et al., we store the value range for each 4-cube block of data, which we use to tell us if a block potentially contains the isosurface. So that would be these highlighted here. However, since we never store the full decompressed volume, it's not sufficient to decompress just these highlighted blocks because we'd be missing data that we need for the dual grid. What I mean is that block A, shown here, shares vertices with its neighbors B, C, and D on its dual grid, and so we actually need these data from these blocks as well. So instead, to check if a block is active and has to be decompressed, we actually check if the union of it and its neighbors' value ranges contain the ISO value. If it does, then the block has to be decompressed. This test is done independently in parallel for each block, since we pre-compute and store the block value ranges in a single storage buffer ahead of time. So our final block list is actually those shown in B, which we mark in the list M active. Given our previous cache state for computing the yellow surface, we need to decompress and cache any new blocks from this active list to compute the current surface. So in this case, that's just block 8, which I have highlighted here. So let's step through our LRU cache update and see how it works. So each substep's shown here in C, so CI, CII. Each one of these corresponds to one or more GPU kernel dispatches or parallel primitives. And I'll keep the previous cache state here on the left as a reference. So first we increment the age of all the slots in the cache. Next we run a thread for each block that marks whether that block is needed for the current surface that we're computing, and it's in the cache, or whether that surface, that block is needed for the surface and is not in the cache, so we mark it as new. Or if the slot has a block in it, but that block is not required for the current surface, we would mark its slot as available, making it a candidate for eviction. In this case, we don't have any blocks that are going to be evicted. We just have one slot that was already unoccupied and one block which is new. That's block 8. We perform a prefix sum and stream compaction on these two arrays, M available and M new, to get lists of the IDs of the available slots and the blocks. So that's I new is the new block IDs, I avail is the new slot IDs, and we also compact the slot ages, the available slot ages, which we use to perform a sort by key here to get the slots sorted by decreasing order of age. We then assign each new block that we're going to decompress to a slot in the cache. So I slot tracks for each block which slot it's stored into. So block 8 is stored in slot 6, and S block stores for each slot which block is stored in it. So block 8 is stored in slot 6. We also reset the age and unmark that slot as available. Finally, we decompress the block using our WebGPU ZFP decompression kernel and output it to the slot in the cache. With all the blocks that we need decompressed, we then compute which of those blocks will output vertices. For example, a block might be made active because it's needed to provide data for a neighbor, but it may not actually contain the surface itself. So in this case, only blocks 0, 1, 2, and 5 are actually going to output triangles for the surface. We then compute the output offsets for these blocks. This is done using a thread group local scan to compute the per voxel offsets, but we only save the total number of vertices that will be output by each block and perform the prefix sum over that. We don't ever save or do a global scan on the per voxel offsets. And finally, we output the vertices to the offsets using the block offset as a base and the recomputed thread group scan as the offset for the voxel. We conducted an extensive performance evaluation of our algorithm. We evaluated it on datasets ranging in size from 67 megabytes to 1 terabyte before compression, and in the benchmarks we cover 16 million voxels to 1 billion. We evaluated on both nested and turbulent sheet surfaces, which have different cache behaviors. So nested surfaces are kind of like the skull or the foot. These are like MRI scans where as the surfaces at lower ISO values contain those at higher ones, whereas the turbulent sheet surfaces are more like a crumpled sheet that moves, say, from left to right, where the surfaces don't really contain each other, but they occupy neighboring regions of the domain as you move the value up or down, but are not really coherent with each other when you sample randomly. And we evaluate on 3 common user interaction modes, so picking random ISO values to kind of find what's interesting, sweeping the ISO value up or down to explore neighboring ISO values. We run our benchmarks on the Surface Pro 7 with the integrated GPU and a desktop with an RTX 2070. And we find that for most cases we frequently operate in cache and can provide fast recomputation of the surface. As mentioned before, the random ISO value benchmark on the Miranda and DNS is especially tough because they're very cache unfriendly in the structure of the data, and you see that we have a pretty low cache hit rate on those and lower performance as a result. However, on the sweep up and sweep down benchmarks for those, we have pretty good cache hit rates and pretty good performance as well. I'll only briefly touch on rendering performance since we're just rendering a triangle soup, but in all cases we achieve interactive performance across the tests and even on some quite large meshes. I'll wrap up with a roadmap of challenges that we should focus on to make it easier to bring SciViz to the browser. So I hope that as a result of this talk, you're convinced that the browser is becoming a capable platform for powerful SciViz apps, and it's worth considering. In terms of easing deployment and development, a community effort to recompile widely used native libraries to WebAssembly would be great. Bringing stuff like VTK to the browser. And similarly, we need something like VTKM or Thrust providing GPU parallel primitives through WebGPU to make this easily available. Thanks for your attention. The code and supplemental material and paper are online at this URL. If you have questions, you can contact me via email or Twitter. And I'd like to thank the funding sources that supported this work and colleagues who provided data and feedback on it during the process.
You're muted.
Oh.
You're muted. Ah. Okay, thank you very much, Phil, for the great talk. We have some time for questions. Please post questions in the chat, either on YouTube or on Discord, if you have a question for Will. Maybe I start with a question. Can you say a bit more about how data streaming of blocks work? And are you using memory mapped files, I think? Can you explain it a bit more and how fast it is and what the latencies are?
Yeah, so it's not really streaming the data from, or like it's in the browser, so I don't really have a memory mapped file. So I stream the entire compressed data set and load that compressed data set onto the GPU. So you have the entire compressed data in memory available to use, and then to decompress on the fly as you need. So it relies on, your compressed data set has to fit fully in the GPU memory plus what you'll need to compute the surface. Yeah.
Okay.
Yeah, so right now there's no out of core stuff or interaction with the host to load data that, say, would be too big compressed to even fit on the GPU.
Yeah, okay. Do you think it would be worthwhile to stream data from the server? You do it locally right now, right? I think.
Yeah, right now it pulls from just like on file, but you could also download the data from the server. And I think, yeah, like it would be worthwhile to have something, it's kind of what I'm looking at next, is like where you can request different blocks of data at different resolutions. something. So one of my lab mates, colleagues, is presenting a paper later in the week about a file format for this kind of variable precision resolution format. So you could have your server that you can query the data at variable precision or resolution, depending on what you need, and upload those to the GPU to decompress and isosurface. So then you would have more interaction between the host and the GPU, and would be able to handle much larger volumes than you'd be able to fit.
Okay, cool. And what's the overhead of figuring out which blocks you need? Does that take a long time? Or?
No, it doesn't take too long. So at the start, when we first load the data set, I go through and like pre-compute the value range of each block. So then we just have a GPU kernel, like a parallel 4, that goes over all these and checks, is the range of this block in the range that we're trying to, does it contain the ISO surface range that we want, or the ISO value, and then marks those blocks as active. And then we do a stream compaction, like a prefix sum and stream compaction to get the IDs of all the active blocks.
Okay, great, thank you. So if you have questions, please post them in the Discord chat. Or wait a bit.
Yeah, I do see someone typing in the Discord. I also have it open over here, but I don't know if they'll post anything. Oh, okay.
Okay, so there's a question by Lutz Hoffmann. Could you elaborate what needs to be done to get existing C, C++ code to compile to WebAssembly? What kind of code just compiles without modifications, and what causes problems?
Yeah, it will depend some on like the libraries that you use. So like there's not, I think it's changing now, but like there's not really threading support in WebAssembly. Like there's these things like web workers on the browser, but they're kind of in a state of like enabled or disabled for security reasons. So like if you're using like threads, right, that's usually can be a problem. If you're using, like x80, like kind of native specific instructions, or you have like SSE or like vectorized code that you've handwritten, that will probably not work well either, right? Because there is like a WebSymd extension in progress, but it's also not very widely available. But most stuff that you're using as portable things will be available, like to run. Yeah.
Okay, cool.
Yeah. I'll advertise the other talk. The talk that I mentioned is Thursday, October 29th at like 1:15. Yeah. So that will be about the data format. So eventually we would look at rendering this kind of format in the browser, which will be pretty exciting. Yeah. But I would think most, like Mscripten is pretty mature now. So like most, if your C or C++ code is portable, it will probably compile. Like with losslib and libtiff, I think like losslib just compiled directly, and then libtiff needed like some small tweaks to how they were defining enums or something, but it was pretty easy to do. Yeah.
Mm-hmm. I think it's amazing that this works.
Yeah.
Very
yeah,
cool.
it's incredible. Yeah.
Okay. Do we have other questions? I don't see anything in the chat right now. Okay, if not, then yeah, thanks for the great work. It's really nice, great talk, amazing work, very impressive. Thank you very much, Will.
Bye.
So the next talk will be Cinnamon Darkroom, a deferred rendering framework for large-scale datasets. And the authors are Jonas, Lukasczyk, Christoph, Garth, Matt Larsen, Vito, Engelke, Ingrid, Hotz, David Rogers, Jim Ahrens, and Ross Maciejewski. And they are from the Arizona State University, from TU Kaiserslautern, from Lawrence Livermore National Labs, from Linköping University, and from Los Alamos National Labs. And Jonas will give the talk. We're looking forward. Here's Jonas.
Everyone, my name is Dr. Jonas Lukasczyk, and I'm going to present Cinema Darkroom, a deferred rendering framework that enables high-fidelity post-hoc visualization of large-scale datasets. For example, the image you see here in the title slide was completely generated just based on two depth buffers, one for the isosurface and one for the extrema, where the entire lighting, edge highlights, color mapping, and depth of field were computed in image space. In a nutshell, Cinema Darkroom flexibly renders geometry buffers that have been stored at simulation runtime in a cinema database. These geometry buffers can contain any generic shading information, such as depth buffers and data textures. Cinema Darkroom then passes these geometry buffers into a flexible shading network that features screen space ambient occlusion to approximate lighting, screen space depth of field to enhance depth perception, image-based silhouettes to highlight edges, and many more image-based shading techniques, where the user has complete control over the creation of the visualization pipeline through a user-friendly node editor. The system is also designed to be easily extendable by, for example, adding custom shaders with minimal overhead. But before we dive deeper into Cinema Darkroom, I want to give you a quick tour of the history of image-based in situ visualization, which motivates our work. Our system is rooted in a core dilemma of high-performance computing, namely that the capability of computing hardware grows much faster than the capabilities of the storage and network infrastructures. So supercomputers can produce unprecedented amounts of data, but due to bandwidth constraints, it is infeasible to transmit all that data through the network or store it to disk. So we need to carefully select what we push through the I/O bottleneck, where the overall goal is to store as less as possible while at the same time enabling as much flexibility as possible during post-hoc exploration. Of course, a visualization is an essential part of post-hoc exploration, so one central question becomes what to store in order to visualize the simulation state after it is no longer available. Ahrens et al. Proposed to solve this problem by generating visualizations at simulation runtime and then storing them in a so-called cinema database. Their approach is based on the rationale that no matter how big the data is, at the end visualization happens on a viewport with a fixed number of pixels. So they propose to store image samples of the parameter and visualization space, where the parameter space consists of different time steps, ISO values, persistence thresholds, and other analysis parameters, while the visualization space consists of camera positions, clipping planes, transfer functions, and other rendering-related options. The resulting image databases are several orders of magnitude smaller than the data they are derived from, and they can be interactively browsed post-hoc along the sampling axes. Cinema database explorers, such as the one shown here, can therefore emulate real-time interaction with datasets of any size by simply snapping to the next available sample point. However, the flexibility of post-hoc exploration is obviously limited to the samples stored in the cinema database, though this approach requires a lot of foresight about suitable samples, especially in regard to the visualization space, like where cameras should be placed, what color maps should be used, how to light the scene, and so on. Every decision made in this step has a significant impact on the quality and flexibility of the post-hoc exploration. The concept of deferred rendering can mitigate this problem as it decouples the information required for shading, such as depth buffers and data textures, from the shading itself, in which one needs to determine suitable color maps and lighting settings. In the context of in situ visualization, deferred rendering can be used to only store the underlying shading information, collectively referred to as geometry buffers, in the cinema database, and postpone final shading to the post-hoc exploration phase, at which point visualization parameters that were not known a priori can now be interactively adjusted. The latest cinema specification provides guidelines on how to actually store geometry buffers in a cinema database. On a personal note, I still have the impression that many people who could definitely profit from using cinema databases are still hesitant to integrate them into their projects. I guess the primary reason for this is that they think cinema databases require a lot of overhead and special data formats, but cinema databases are deliberately kept as simple as possible. In fact, a cinema database is just a folder with the extension .cdb that can contain any kind of data product, for example JPEG images, VTK files, raw binary data, and so on. The only special thing is that the folder has to contain a data.csv file that has a column named file that records the relative path to all data products, and any number of additional columns that record associated sample values of the data products, such as their corresponding cycle time, object ID, and whatsoever. This CSV file is consumed by database explorers to understand the content of the database and the axis on which it can be browsed. The example database on this slide just contains 4 geometry buffers in the form of VTK image files, where each buffer is associated with a timestamp and an object. That is all there is to create a cinema database. Of course, you can make the structure of the database as simple or as complex as necessary for your project. For example, if you want the user to be able to rotate the camera, then you need to store geometry buffers for different camera angles and record for each buffer the corresponding camera angle in the CSV file. Any intelligent cinema explorer will understand this and then allow you to rotate the camera with your mouse. The topology toolkit actually features a powerful cinema database adapter and even features a VTK filter that can generate geometry buffers. This filter is called TTK Cinema Imaging and takes 2 inputs, a triangulated object that is supposed to be depicted and a sampling grid that records the camera positions and calibrations. The filter will then generate for each camera a geometry buffer that contains a depth buffer and a data texture for any array stored on the input triangulation. In advanced scenarios, the geometry buffers can also store additional information, such as ambient occlusion, motion blur, or light factors. However, as I will show in the rest of the presentation, the depth buffer alone often suffices to produce high-quality visualizations that are on par with path tracing. The database adapter can then be used to store and later retrieve the geometry buffers. For more details on how to use cinema databases and TTK, I refer you to the TTK webpage. Now that we know why and how to create cinema databases containing G-buffers, we revisit the front end of Cinema Darkroom that processes these databases. The main interface element is a common node editor, just like the one used in Blender or in Vivo, which enables users to create a pipeline graph. Individual nodes of the graph correspond to shaders or other filters, where input and output parameters are shown via ports. The output of one filter can be used as an input of another, which is indicated by an edge. The pipeline follows a push model, thus as soon as a new input value is available, the filter updates its output, which then triggers an update of filters that use the updated output as an input, and so forth. Values of unconnected inputs can also be adjusted via widgets that are shown right next to them. The interface also contains a render view that shows the output of a selected filter. Regarding its actual implementation, the front-end is completely written in JavaScript and WebGL, where the front-end can either directly import a cinema database or connect to a ParaView server via a WebSocket to retrieve G-buffers. G-buffers and intermediate renderings are then passed along the network as frame buffer objects. If a filter corresponds to a shader, then its inputs are automatically passed to the shader as uniforms. Cinema Darkroom features several image-based shading techniques, from rudimentary operations such as color mapping and scene compositing to advanced shading effects such as screen space ambient occlusion to approximate global illumination and screen space depth of field to enhance spatial perception. Moreover, one can easily add new techniques to Cinema Darkroom with minimal overhead. In the simplest case, developers just need to create a single JavaScript file in which they inherit from the general filter class, supply a fragment shader, and specify the input and output parameters of their filter, where the input parameters are automatically passed as uniforms to the fragment shader. Something I'm really excited about is that we are also currently porting everything into a ParaView plugin. Actually, all image-based techniques are already converted into VTK image data filters, but ParaView was never designed to build complex pipelines, which makes this process rather painful. So we are now working on a separate plugin that will provide a node editor for ParaView, in which it will be as easy as in the web-based front-end to build shader networks, with the additional advantage, of course, that you can also use it to design any pipeline. Okay, now let's have a look at some results. In the simplest use case, one just needs to apply post-hoc color mapping. Here you can see a simulation of a two-material inertial confinement fusion problem in 2D that was simulated at the Lawrence Livermore National Laboratory. Instead of storing the raw simulation data, their scientists generated a highly time-resolved cinema database consisting of over 2,000 scalar images with a resolution of 2,048 squared pixels. This database is roughly 20 times smaller than the original simulation data, and that is without compression. Of course, prior to the simulation, it is not clear what color map will be most suited to visualize the data, so this needs to be determined interactively during post-hoc exploration. Due to Cinema's simple file system-based API, it was trivial to hook up the database to Cinema Darkroom and apply different color maps. This example shows a computational fluid dynamic simulation of a jet entering a medium at rest, where the simulation domain consists of a regular grid with two scalar fields, the velocity and vorticity magnitude. During the simulation, we generated a cinema database consisting of two individual cutting planes, a contour, and streamlines that were seated on the contour. If a cinema database contains depth buffers of individual objects, as in this case, then it is possible to dynamically compose them post-hoc, where the user can control via the shader network which elements are shown and how they should be colored. If we additionally know the camera calibration that was used to generate a G-buffer, in other words, the position, orientation, and view box of the camera, then we can actually recompute the 3D world location of each pixel. Here, in this example that shows a contour of the entropy field of the Richtmeier-Meshkov instability, we recomputed the 3D location of every pixel that depicts the contour and color the pixel by its world Z coordinate. So this height field was not stored in the cinema database, it was reconstructed post-hoc. This can even be used to project new geometry into image space. In this example, we computed at simulation runtime via TTK the location of persistent maxima of the height field defined on the contour. This list of point locations was then used during post-hoc analysis to project spheres into a new depth buffer, which was then correctly composed together with the depth buffer of the contour. To correctly perceive 3D datasets, the human visual system needs depth cues, most importantly in the form of shadows. However, correctly lighting a scene is very tricky, even if one can perform the complete rendering interactively on a desktop machine. In recent years, path tracing techniques have been established as an excellent tool to light a scene, especially in the context of scientific visualization. However, path tracing still requires correctly positioning light sources and tweaking parameters such as the exposure and ambient occlusion factors. One also has to take care that the lighting doesn't interfere with the expressiveness of the visualization, by, for example, darkening regions that contain important scalar field information. Getting good results usually involves interactive exploration, which we simply cannot do in situ use cases. With deferred rendering, however, we can adjust lighting interactively during post-hoc exploration by using techniques such as screen space ambient occlusion and screen space depth darkening. These techniques, of course, only approximate global illumination, but they can still achieve excellent results, and they enable illustrative effects that cannot be achieved with conventional path tracing, while requiring much less computational effort. The scene shown on this slide consists of complex streamline geometries, which are shaded via the same SSAO technique, but at 3 different sampling radii, which are specified in % of the image height. As you can see, small radii highlight local details, while large radii approximate lighting more globally. This radius can be adjusted interactively in Cinema Darkroom based on the visualization task at hand, and it is even possible to combine different SSAO outputs in the node editor to combine shading at different scales. However, SSAO of course also has its limitations. The current SSAO technique used in Cinema Darkroom is optimized for surface-like objects. This technique still works well for the streamline example, but fails to produce adequate depth cues for scenes with high varying depth buffer values, such as the ones that occur in particle visualizations. In the future, we plan to integrate SSAO techniques that were specifically developed for such visualizations. In this final example, I want to highlight again the quality of visualizations that we can get out of a deferred rendering pipeline. Here you can see a porous limestone ground sample taken from South Florida, as well as the path of water as it would run through the cavities of the stone. The stone is colored according to its height, and the water path is shown via blue streamlines. Currently, the entire shading is done again via SSAO, which doesn't do a bad job, but it's still hard to notice details, the spatial relationship between streamlines and the structure of the stone. By additionally applying image-based silhouettes, perception improves drastically, as edge highlights help us to recognize shapes and their spatial arrangement. Spatial perception can be improved even further via screen space depth of field, although we recognize that it is a controversial effect. But if used correctly, it is our belief that it can greatly improve the quality of visualizations by automatically highlighting a part of the scene while still providing context. Like in this example, it nicely highlights the tips of the streamlines and creates the illusion that the streamlines are coming towards the observer. In conclusion, we describe a deferred rendering framework for high-quality visualization of datasets of any size. In the context of in-situ visualization, our framework can be used for interactive post-hoc visualization based on a cinema database that has been generated at simulation runtime. In the future, we plan to integrate more image-based shading techniques, and it is our hope that Cinema Darkroom can establish itself as a unified benchmark environment for post-hoc visualization, where the research community can easily contribute new techniques and compare against existing approaches. However, CT is currently limited to G-buffers that depict fully opaque geometry. This notably excludes post-hoc volume rendering, except in its most basic form of directly storing colored images in the cinema database. Of course, we are also working on the ParaView integration, and I hope that at the time of the VIS conference, there already exists a ParaView discourse thread that pushes the development of the node editor and Cinema Darkroom forward. So where can you get Cinema Darkroom? At the time I recorded this video, the plan is to ship it together with the topology toolkit, since TTK already has a powerful cinema adapter. But as teased before, we are also trying to ship it as a standalone plugin to make it more accessible. So please check out my webpage, the TTK webpage, and the ParaView discourse channel on any updates. Of course, I'm also happy to answer any questions, and if you want to get involved, please contact me. This concludes my talk, and I thank you all for your attention. Goodbye. Hi, can you hear me?
Yes.
Okay, great.
Thanks a lot, Jonas, for the great talk. This is really nice work.
Thank
you.
you.
We have time for questions. Please post questions in the chat if you have any. There's a question already by Peter Risto. How does cinema handle isosurfaces with a high degree of occlusion? For example, when no camera can capture an image of a part of the isosurface?
Yeah, so that's a common problem of image databases. So what you would have to do is either record the isosurface as blocks of also individual depth images. You can toggle on and off, like peeling through them. So there are some approaches that can already do this for like what Will mentioned earlier. If you have isosurfaces that have like nested structures, you can just depict them part by part, and then you can just toggle them on and off. And Cinema Darkroom would support actually toggling on and off individual layers interactively, since the rendering is almost negligible in the performance overhead.
Okay, thank you. So how do you handle animations? Do you have to transfer all the animation frames, or can you stream them on demand, or how is that handled?
Yeah, so basically the main point of Cinema Darkroom is that it has like two parts. The one part is like where we do the post-hoc visualization of all those elements we stored in the first step in the database. So if you want to record a video, an animation, and then render the animation, then of course you need the keyframes stored in the cinema database. And then you can just stream those into your rendering framework. But if you want to do interpolation between the keyframes, that's not supported yet.
Mm-hmm. Okay, great. If you have questions, please post in the chat. So I have maybe
also free.
Sorry, yeah.
Sorry, I was just saying, like, please feel also free to ask me about this pet project of the node editor in ParaView. But yeah.
So I have maybe some future work questions. So you cannot handle transparent layers, I think, currently, right? I mean, that's maybe related to the nested isosurfaces. How would you handle transparent layers, or what just depth peeling, or?
Yeah, so that would be the next thing. I mean, basically all those techniques that were derived for this classical rendering on the desktop machine, when you still have all the data available, can be sort of translated or transferred into this post-hoc visualization concept. So for example, death pilling is a good example where you can just compute that in situ and then only store the information necessary for that operation and then do that post hoc.
Mm-hmm. And do you think it would be possible to reuse views? So if cameras that you haven't pre-computed, to warp them, or do you think the quality might not be good enough, or how would you handle that or approach that?
Yeah, so 2 years ago at LDAV, we had this paper called Voidga, a view approximation based image interpolation technique or something. And basically this tries to approximate views in between stored view angles. And there are two rules of thought here, basically. One is to either do an interpolation of the images or to do an approximation of the geometry and then render the approximation of the geometry. And we can currently only do the second, but yeah, there's a paper in submission where we try to do the first.
Okay. So would you have to store additional data, or would you just use what you have in the cinema layers?
So for the geometry approximation, we can do this right away with only the depth buffers. So the second step already works. And if that first approach would work out, we would only need to have color images of the individual samples. And then, there are a lot of neural network techniques out there already that just take 2 or 3 color images of subsequent frames and then do an interpolation between those. Yeah.
Yeah. Okay, great. So I'm not sure if we have an additional question. Somebody's typing. Let's wait for a bit.
Yeah.
So what are in general the next steps or this is really, really great work, right? But you can do a lot of stuff in addition, maybe. So that what would be the most important?
Yeah. So right now everything is available as this JavaScript plugin, but like who uses a third tool if they have to, right? So we are now trying to move at least all of the stuff into a widely used tool, ParaView. When basically all these individual image processing steps are available as VTK filters, then I think a lot more people are willing to use it. So consider the JS, as the JavaScript system as basically a prototype of that's what we are trying to do. And then the VTK cinema imaging stuff will be the final product.
Mm-hmm. So there's a question in the chat from Ellen. Screen space techniques are resolution dependent. How does cinema handle buffer resolution?
Yeah, well, I mean, if you only have an 8x8 image, then of course screen space occlusion won't give you anything. So yeah, we are restricted to what's in the cinema database. Although, there are some other things we could do, like, for example, do neural network-based upscaling and stuff. But yeah, at the end, every time you deal with cinema databases, you are restricted to what you stored.
So you choose a fixed resolution, I guess.
Yeah.
Let the user choose a fixed resolution.
Yeah. So preferably one that is big enough so that you can have nice results, but at the same time not to blow up the size of the database.
Mm-hmm. Okay, great. So yeah, if there are no more questions, thanks a lot. This is really nice work. Thank you very much for the great talk.
Yeah, thank you for all the questions. Yeah. All right. Bye-bye.
Thank you.